You ever stop and think about the invisible architecture that's running our entire modern world? From the stock market to your social media feed, it's all powered by one fundamental concept: algorithms. I mean, how does your GPS instantly figure out the fastest way home, dodging traffic you don't even see? Or how does a streaming service seem to read your mind, suggesting that perfect movie for a Friday night? Nope, it's not magic. It's a very specific and very clever kind of logic. So for this explainer, we went looking for the key to it all, and we found it right here, inside a university course syllabus called Design and Analysis of Algorithms. This thing? It's the blueprint, the training manual for building the very logic that shapes our digital lives. And the course rationale just puts it perfectly. It says that one of the most long-lasting contributions of computer science isn't some gadget or app, it's the refinement of the algorithm. See, it's not just about code, it's a whole new way of thinking, one that really took off the moment we built machines that could calculate for us. Okay, so let's try to do that. Let's start thinking in algorithms. What are they, really? Let's forget all the complicated jargon for a second. At their core, it's a beautifully simple idea. An algorithm is just a set of well-defined instructions. Seriously, that's it. Think of it like a recipe. You give a computer your ingredients, that's the data, and a step-by-step method, and bam, it produces a result. Could be a sorted list, could be the shortest route, could be a batch of cookies. The logic's the same. But hey, as anyone who's ever tried to cook knows, not all recipes are created equal, right? Some are fast, they use just a few ingredients. Others are, well, they're slow and messy. In computer science, it's the exact same deal. The best algorithms are the ones that are both super fast and incredibly efficient. And this brings us to how computer scientists actually measure how good a recipe is. They're obsessed with two key things: time complexity, which is basically just how long does it take to run, and space complexity, which is how much memory does it hog. The holy grail is always to get the best possible result using the least amount of time and space. Now, to solve all these different problems efficiently, programmers don't just start from scratch every single time. Oh no. They have a whole toolkit of proven strategies, or paradigms, for designing these recipes. Let's check out a few of the big ones. First up, a total classic: divide and conquer. And it's exactly what it sounds like. You take a massive, complicated problem and you just break it down into smaller, more manageable little pieces until they're so simple you can solve them easily. This whole chop-it-up strategy is the secret sauce behind some of the fastest ways we have to sort huge amounts of data, using methods like merge sort and quick sort. It even tackles really complex geometry problems, like figuring out the most efficient boundary to draw around a set of points. Next, we've got the greedy method. This approach is all about making the best possible choice at every single step, hoping that a series of these good enough for now choices will lead to the best overall solution in the end. It's this what's best for me right now thinking that powers your GPS to find the shortest path. It's also used to compress data super efficiently with things like Huffman codes, and to design networks at the lowest possible cost. It's incredibly fast, but there's a catch. It doesn't always guarantee the absolute perfect answer for every single type of problem. All right, our third strategy is dynamic programming, and this one is just incredibly powerful. It also breaks down complex problems, but it has a really clever twist. It remembers the answers to the smaller problems it's already solved. This whole don't repeat yourself approach is a game changer. It stops the algorithm from wasting time recalculating the same thing over and over, which makes it perfect for really complex optimization puzzles. This is the go-to tool for tackling huge challenges like the famous traveling salesperson problem, and we're going to come back to that one in a second. Because this brings us to a totally fascinating edge of computer science. What happens when a problem is so mind-bendingly hard that even our best strategies can't find a fast solution? Well, welcome to the unsolvable frontier. So let's go back to that traveling salesperson problem. It's so simple to explain. Just find the shortest possible loop that hits a list of cities just once. Sounds easy, right? Okay, but what if you have thousands of cities? The number of possible routes just explodes. We're talking a number bigger than all the atoms in the known universe. So how on earth do you find the single best one without checking every single option? And the answer is, we don't know if a fast way even exists. This problem belongs to a special class called NP-complete.
Think of them as the final bosses of computation. They all share this bizarre property. If you could find a fast solution for just one of them, you could use that same trick to quickly solve all of them. Finding that solution is one of the biggest unsolved challenges in all of computer science.
So we've gone from simple recipes all the way to the edge of what's even solvable. But how do you go from all this theory to actually building something? How do students learn to actually wield these powerful tools? Well, they get their hands dirty. The course's lab sessions show students spending weeks implementing these exact ideas. They're in there building programs using the greedy method, they're coding solutions with dynamic programming, and they even get to wrestle with those monstrously hard problems in a practical, hands-on setting. So after all of this, what's the real takeaway? Is it just about memorizing a bunch of different sorting algorithms? No way. It's about something much, much bigger than that. The real goal of a course like this isn't just to learn a list of algorithms. It's about mastering a systematic way to look at any complex problem, break it down into its core parts, and then build a logical, efficient solution from the ground up. It's a way of thinking that goes way beyond coding. It's about transforming you or anyone who studies this into a much more skilled and rigorous problem solver in pretty much any field you can imagine. These strategies really are the engines of our modern world, but at the end of the day, they're just tools. The most important part is the human creativity that decides which problems are actually worth solving in the first place. So, the only question left is, what problem will you solve?